So I did want to go over one more thing here with the loops. So let me actually move this over just a little bit. I guess I could erase it. I'll just move it. Move that over. My little loops. Move this over here. Okay, so I want to look at what happens. Or, I mean, how does a magnetic field behave? When you are far from the loop. So essentially we're looking when Z is much, much greater than R. Okay, well, here's our equation up in the corner, right here. And if Z is much, much greater than R, it's, this, even though they're both squared here, R squared plus Z squared, this Z is going to overwhelm this R squared, right? The Z squared is going to be much, much bigger than this R squared. And so that R squared is not going to have a whole lot of weight, to be added to it. So this loop or this magnetic field equation kind of gets simplified, and we get this. Magnetic field becomes, I still have my mu0, still have my I. Let's see here. So I have my R squared. And on the bottom, it just becomes 2Z cubed. And we're just talking about distance here. Right. The direction will change whether you're going to positive z-axis or negative z-axis. No, actually, I take that back. It'll always be in the for our example that we just did. It'll be in the positive k hat direction. Okay, so I'm not quite done with this. I'm gonna multiply 2 pi to the top and bottom. There's a reason why I'm going to do this, because there's something similar that we've seen before. Okay, so this becomes mu0 2 times I, pi r squared over 4 pi z cubed. All right, so why am I writing this? It's because this part here, let me highlight this. Okay, that part right there. Oh, you know what? I don't like that highlighter. I was trying something new, didn't work. So I'm just gonna go back to what I usually do. This part right there. So that's current times in pi r squared. Well, what's pi r squared, right? It's area. So it's current times area. That comes up so much. We call this the magnetic dipole moment. Okay, so this is the magnetic dipole moment. And it's, okay, so let me apologize in advance for using the same symbol, but that's what it is. Mu, not mu0, just mu equals I times A. Okay, so what this is telling us is that when you go very, very far from this wire, here's this wire, the magnetic field that's coming from this looks like that. And it's just it becomes a dipole. It's just like a north and south. It just looks like a magnet, right? You would get the same thing if you had a magnet and the north side was here and the south side was here. You get exactly the same thing. Okay, so we get an equation for a magnetic field in terms of dipole. Mu0 over 2 pi. I don't know why I multiplied 2 pi. Anyway, 2 pi over 2 pi. Times mu over z cubed. Okay, Which, oh, no, sorry. I do have a 2. This is 4. I simplified it, but it should be there. Okay, which actually kind of looks similar to something we saw for electric field. We saw the electric dipole a little while back. Electric dipole was this, 1/4 pi epsilon 0 times 2p over z cubed. So really similar to a electric dipole. We get a magnetic dipole, different symbols, obviously, or different, what do I want to say? We get different variables, different constants. Right, this one has mu0. Obviously, we have epsilon 0 here. You got mu for your dipole moment, p for your electric dipole moment, but you have really similar similar forms. Right, it's supposed to be a 4 pi. Okay, so anyway, just wanted to talk about that because it's kind of neat to see that when you go further and further away from these coils, you get back that dipole behavior. It's just acting like a magnet, essentially. All right. So I just wanted to cap off our last discussion with that. All right, so let's look at the effects now, effects of a magnetic field on a charge, okay, which is essentially magnetic force. So we're not looking at sources of magnetic field. We're not seeing how charges create a magnetic field. For these examples, I'm going to just assume there's a magnetic field there that's created by something, a magnet, a wire, something like that. So I have this magnetic field already here in space. There's my magnetic field. And I'm going to have a charge here. Let me put a charge there. There's my charge. Now we see a couple of behaviors here. Let me put this. So placing a charge in the magnetic field. So if the charge isn't moving, which is the case now, there is no magnetic force. So nothing happens to that charge. If that charge is not moving, it's just stationary, then guess what? It's just going to stay stationary. Doesn't move, doesn't feel a force, nothing. So let me change the situation. What if I had a speed now of the charge, and I'm going to put the speed in the same direction as the magnetic field, so going up. What happens then? Well, back here. The charge is moving in the same direction as magnetic field. Still no force. Okay. So I was going to do one of these. Okay, so yeah, still no force there. So that's that. We don't see anything there. Well, okay, I'm going to change it to one more situation here. Oops. And I'm going to add a velocity this way. Okay, so if I do that, so if the charge is moving, it's moving at some angle with respect to the magnetic field, we see a force perpendicular, a perpendicular force. Okay, so it's kind of interesting that we kind of see that the force is actually going to be pointing here for this positive charge. The force that results is kind of it's kind of hard to draw here. is coming out of the screen. So let's draw a dot. That's my force coming out of the screen, coming out towards you. Okay, so what describes this this relationship that, you know, if the charge isn't moving, so if the charge isn't moving, clearly in order for there to be force, it depends on there being a speed, right? If the charge isn't moving, we get no force. So it has to have a speed, but not only that, it has to have a speed in a particular direction. And so the cross product comes into play again. So magnetic force, I'll put FB, equals your charge times the speed, or times its velocity, I should say, cross product with the magnetic field. Okay, so this is magnetic force. You get zero force. And remember another way of writing this, if you want to do it kind of the algebraic way. The magnitude of V times the magnitude of B times sine theta. Where this is the angle. Okay. All right, so this cross product kind of is a great tool that describes what we see with forces or charges moving in magnetic fields. Particularly that second line there, is the charge is moving in the same direction as magnetic field, still no force, and that's because of the angle, right? If that angle, this angle right here, if that angle is either 0 or 180, right? So remember, there's the angle between V and B. If the angle between velocity and magnetic field is 0 degrees, which was the case earlier when I had it going in the same direction, or 180 degrees, so in my picture here, if that velocity was going down, then you wouldn't get a force. You have to, there has to be some kind of angle between V and B other than 0 and 180 for you to get a force here. Okay, so let's try this out in a different kind of different situation. So looking at this from a different angle, let's say I have the magnetic field going into the page here. So here's a region of space where the magnetic field is going into the page. Okay, and then I'm going to have a charge. So do you want to make this positive or negative? We'll do a negative in a second. Let's just keep it positive. So I have a charge going like this. Okay, so let's get familiar with this and do a right-hand rule to see what direction it's going to go. Okay, so let me come up on the screen here. Okay, show you guys. All right, so same right-hand rule as before, where if you want to do the chicken claw, remember the chicken claw, your thumb always represents, oopsie. Your thumb always represents your first vector, and your index finger always represents your second vector. So when I do the chicken claw here, my thumb is representing velocity in this case. My pointer finger is representing magnetic field. Okay, so I'm going off what I see in my equation. My thumb is my first vector, velocity, and my pointer finger is my second vector, which is magnetic field here. The middle finger here is representing force. Okay. All right, so let's line this up. So the thumb, if you look on the screen, it's going to the left. So I'm gonna put my thumb going to the left. Okay. And then this is all from your perspective again. The magnetic field is going into the screen, right? That's what the X represents. So going into the screen, I know you guys can't see it from there, but my index obviously pointing into the screen there. And now you can may see it from this perspective, my middle finger is going down. Right, so that would mean my force is going down. Okay, so I'll do that one more time. Thumb is going to your left, pointer finger is pointing into the screen, and your middle finger, as a result, should be going down. Okay, I hate doing that. Well, I hope it's helpful. Okay, the other way I would have done it is just like use your whole hand. Put your whole hand along V, curl towards B. So B is going into the screen, so curl towards into the screen. So if I do that, much easier, I guess. Going to that, I'll get my thumb pointing down. Okay, so velocity going this way, curl into the screen, and you get your thumb pointing down. Okay. Well, I know it's a little tricky teaching on the Zoom there. I can't really show you from my perspective, but I'm doing it from your perspective. Okay, so hopefully, if you're following what my hands are doing from your perspective, it should be okay. All right, let's see. So now we have magnetic force going down. All right, so you kind of have to go back into your first year of physics or your first physics course. We have velocity and force perpendicular to each other. When have we seen that? Velocity and force being perpendicular to each other. Oh, doesn't look familiar? Well, let's think about what's going to happen to this velocity. Force is going to pull that charge downwards, right? So it's going to change. Eventually, it's going to change the direction of velocity. So let's say it changes direction of velocity. So now it's here. Here's my charge. Here's my charge. Now, what direction is force going? Because force is going to change the direction of velocity. But now, when you change the direction of velocity, your right-hand rule changes, doesn't it? So do the right-hand rule for this scenario. Velocity going down, magnetic field is going into the page. See if you can get the force. What direction is the force going? Yeah, I get it. I get it to the right as well. So we get a force going to the right. And so if you see what this force is going to do, if it's always going to be 90 degrees to your velocity, what we get is that this charge is just going to be moving in that circular motion there. Force being always towards the center. What else? What else does that look familiar to? You have this object going around and force is pointing towards the center. Centripetal, yes. Centripetal force, that's exactly what we're seeing here. Okay, so we see this centripetal force, centripetal force acting on the charge. And what's that centripetal force? It's magnetic force, right? The magnetic force is acting as a centripetal force, causing it to go in a circle. And so if we're looking at centripetal force, we said in our previous physics class that goes MAC, right? Where that centripetal force gives us a centripetal acceleration. And of course, we're talking about magnetic force here. And so that magnetic force, we know the equation, QVB, and it has sine theta, but what's the angle between V and B in all scenarios, in every single step of this motion? The angle between velocity and magnetic field. Yeah, it's just 90. All right, so if we're just looking at 90, sine 90 just becomes 1. So if you're wondering what happened to my sine over here, right over here, well, this is sine 90, and sine 90 goes to 1. So I just need the QVB. So QVB equals MI. Where is that little? Oh, it's not negative. M, and then AC equation for AC is V squared over R, where this R, magnitude capital, where this R is the radius of this circle. Okay. So we can use this to find a couple things. This relationship here, we could use it to find, let's say, the radius of this motion. All right, solving for R, you get QB over MV. All right, so depending on the charge of the particle and the mass of the particle and how strong the magnetic field is and your velocity, all that determines how tight this radius is going to be, or how large this radius is going to be. We can use it to find frequency. Frequency is a little harder. Frequency is 1 over the period. And we could find the period by velocity, right? Velocity, the time. Time is, let me do it off to the side. Right, distance over time, where that distance is a complete rotation, right? One complete cycle. So doing some algebra there. Let me get this. All right, so kind of solving for t there and plugging it in. And then using my equation for R, V over 2 pi QB over MV. Wait, no. What am I doing here? No, I plugged in. Oh, what did I do? Did I do that right? M QB MV. No. What did I do? I don't understand something. I guess I did it right. Oh, there's a lot of algebra to do here. I'm just doing it on my paper really quick and just saying, like, this is a whole bunch of simplification to get what I want, because I want to get rid of the V's, and I can get rid of the V's by, again, using this equation over here, solving for V and plugging it in. So I can get rid of the V there. It's just all this little algebra. I'm just gonna write what I get the final answer once you do all the algebra. There's probably an easier way. I think I just did the long way of doing my my substitutions. So eventually we should get this. It's supposed to be times 2 pi. Okay, so that frequency is related to the charge, mass, that charge over mass ratio, which is really important, B, and then that's 2 pi in the bottom there. Let me write that a little neater. I did say a little neater. Okay. All right, so what we see in both of these equations is that charge to mass ratio, really, really important there. That charge to mass ratio, like things for like an electron or proton, you can't change that, right? You have a charge for a proton, mass for a proton. Those are both constants. So that charge to mass ratio will determine what that radius is, right? And also, I guess, magnetic field, what that radius is, and what the frequency is. Okay. All right. Let's see here. Let's do an application here. Let's do a problem. So there's these things called different things use these, but I'm gonna call it a velocity selector. And what a velocity selector does is that it chooses a velocity of objects to go through. So let me show you how it's drawn, and I can explain how it works. In a velocity selector, you have a parallel plate capacitor. Okay, and you have an electric field from that parallel plate capacitor. Let me see here. Let's do electric field in red. So let's just say my electric field is pointing down. Okay, and what we're going to do, let's say we have a negative particle flying through this. Let me see here. Flying through this through this capacitor. Okay. Now, what would happen to that negative particle as it goes to this capacitor? If there's nothing else to this, you just have this electric field. What would happen to that charge? Yeah. Okay. Good. It should go upward, right? So if you imagine the trajectory looks something like this, right? So it's coming in and it'll start to curve up, right? It'll do something like this. All right, so I want to prevent that. And I want it to go straight through it without being affected by the electric field. Or at least, maybe I should put it this way, I want something else to cancel out that electric force that's pulling it up. Okay, so I'm going to add, so let's see, I can write this. I want this charge to go through without deviation by adding a magnetic field. Okay, so my question is, if we're going to do that, if we're going to add a magnetic field, what direction and magnitude does the electric field, does a magnetic field need to have for this charge to move without changing trajectory? That's bad. Maybe I should put it undeflected. Charge to move through undeflected. Okay, so first let's talk about direction, because direction, we don't need any equations for it. We just have to know how the right-hand rule works. So if I draw my force diagram for this charge, let me see, let me do it in blue. Okay, so I have electric force going up, Fe. If I want this to go through undeflected, right, I need some other force to go down, and so that'll be my magnetic force. I want my magnetic force to go down. The issue is I have the velocity of this object going to the right, and it's a negative charge. Okay, so we're gonna have to figure out through the right-hand rule what direction we want magnetic field to go in order for this to go undeflected, in order for a magnetic force to go down. Okay. Magnetic field coming out of the screen. Actually, there's a couple things that we need to consider. I'm going to work it out with you guys because I don't know off the top. I have to do the right-hand rule myself just to be sure that it would be coming out of the screen. So let's do it this way. All right. So if we're going to do the chicken claw, right? My thumb represents velocity, so my thumb going to the left. We want magnetic force, which is my middle finger. We want magnetic force to go down. Okay. So I have my velocity going to the right. Velocity is going to the rest of my thumb. Okay, so my thumb's pointing to the right, middle finger going down. According to my right-hand rule, this says that my pointer is coming out of the screen. Everyone see that? Or let me know if you want me to repeat that. How do you get your pointer, which represents your magnetic field coming out of the screen? Okay, so thumb, so you're gonna do the chicken claw method. Thumb represents velocity, and that velocity is going the velocity of your charge. Okay, so you're looking at your screen, charge is going to the right, so put your thumb facing or pointing in the right. Okay, So my thumb is pointing to the right. Then I have my middle finger. My middle finger represents force. We know from the problem, let me get my pointer, from what we discussed, that magnetic force has to go down. Okay, so middle finger has to go down. So right there, velocity going to the left, middle finger going down, that leaves my pointer pointing in the pointing out of the screen, right? Coming out towards you. And so you should see that with your own hands. You should have the pointer finger pointing at you. Okay. Now the problem with this is that we're talking about negative charge, and then if you go back to our equation, you have QVB, and that Q is not, we're not talking about absolute value there. If you have a negative charge, that negative is going to flip your final answer. Okay, so there's a couple of ways we could deal with this. One is to literally flip your hand around, right? So if you get out of the screen, then the answer is going to be into the screen, okay, because we're dealing with a negative charge. So you just have to, for negative charges, you have to remember to flip your final answer, or you could use the left hand rule. If you do the same thing for the left hand, you get the answer right away. You don't have to flip it or anything. So I kind of like that way better, using the left hand, because what tends to happen is that, you know, you're doing the problem, you do the right hand rule, and you forget to flip right at the end of it. But it's easier to remember right hand rule for positive charges. Use the right hand rule for positive charges, and then you use your left hand rule for negative charges. Okay, so if you do it for a negative charge, oh gosh, it's gonna be right. So my thumb's pointing to the left. I know you can't see it because my wrist blocks you. Middle finger points down, and then I get my pointer, you know, coming out of the page. No, did I do that right? Going to the left, middle finger goes down. Yeah, sorry, pointing into the page, right, from your perspective, going into the page. Yep. Yeah, I'm doing it from your perspective, and I have to remind myself that. So going to the right, middle finger going down, and then my fingers pointing into your screen here, going away from you. Okay, so yeah, we get into the page. So that would be our magnetic field. So let me draw that in our picture here. So I'm going to add my magnetic field. We know the magnetic field is going into the page here. Okay, so going into the page will give us that force going in the opposite direction. It will give us a magnetic force going down. Okay, so if that's true, what I said, okay, so I'm done with the right hand rule there. So what I said is that FE and FB, right, this is going undeflected, those two forces can't be, they have to be equal and opposite. So I can start writing this. I know their magnitudes are going to be equal. If it's to go through undeflected, this has to be true, right? The magnitude of those two forces have to be equal. Okay, well, we know the equation for QVB, so QVB here. The angle again is 90 here, right? The angle between velocity and magnetic field. So we don't have to worry about sine here. It's going to be sine 90. Sometimes you do have to worry about that sine, but in our example so far, the angle has been 90 degrees. So sine 90 is 1, and then for FE, it's QE, right? I'm not doing all absolute value because, again, we're just looking at the magnitudes. Okay, so let's solve for, let's see, what direction and magnitude does the magnetic field have to be? So if we solve for B, Q's cancel out, and I'm left with the magnetic field, B equals E divided by V. Okay. So we just have to adjust our either magnetic field or electric field so that this ratio holds. Right? If this ratio is going to hold right here, then we'll get undeflected. And notice that it does depend on V. So if let's say the object, the particle is going a little bit slower than the velocity we calculated, right? So let's say it's a little bit slower than this one. What would another particle go? What direction would it go if it was going slower? Well, if that particle was going slower, we would expect something like this. Let's say if it's going slower, FB will not be as strong, right? That you have a lower velocity. That lower velocity will give you a smaller magnetic force. Electric force is unchanged, assuming the same Q, assuming the same charge. But all we're doing is having another particle with equal charge with smaller speed. FB is going to get weaker. So for something that's going slower, this is what's going to happen. Oops. The trajectory is going to look like this. All right, so this is slower. If something is going faster than the speed that we've chosen or we're calculated, then that means FB is really strong, right? With higher velocity, you get a stronger magnetic field, or sorry, stronger magnetic force. And if you get a stronger magnetic force, well, the trajectory is going to look a little different there. It's going to go like this. It's for something going faster. Only the objects that have the right amount of speed will continue in that undeflected direction. Okay, so this is why it's called a velocity selector. You could what this does is it, and also it's independent of charge. But this relationship, it is independent of charge. It just depends on velocity. So only particles with the right amount of speed will go through undeflected. Anyone going slower than that will go up. Anything going faster than that will go down. Okay. All right. Let's see. We'll stop here for today. Next time, we'll look at forces on wires, because wires, wires carrying a current, to be specific. But when wires carry a current, they have charges moving, and those charges moving, they're also going to feel forces. So we're going to look at the magnetic force acting on wires next time, and that should, and we'll start wrapping up chapter 29.